Let's now start solving question. The linear expansivity of brass is 2 times 10 raised to the power minus 5. If the volume of a piece of brass is 10 centimeter cube at 0 degrees Celsius, what will be its volume at 100 degrees Celsius? So I want you to pause it and solve it. After solving it, let's look at the solution. Given that you are given what? The linear expansivity. You are given the initial volume. You know your initial temperature. You don't know your final volume. You know the final temperature T2. The first thing is you are given linear expansivity instead of what? Volume expansivity. You need to convert your coefficient to what? To coefficient of linear expansivity. And what is the relationship? Gamma is equals to 3 alpha. Just substitute it 3 times 2 times 10 raised to the power what? Minus 5 per Celsius, per degree Celsius, then you get this. Now using gamma is equals to what? V2 minus V1 over V1 into bracket T2 minus T1. Make your V2 solve the formula. If you make it solve the formula, you get this. V2 is equals to what? Gamma V1 into bracket theta 2 minus theta 1 plus V1. Now your V2 will be what? The change in length, change in volume plus the original volume. And why are you going to calculate the change in volume? This is it. Change in volume plus the original volume. You substitute the values here. You have what? 6 times 10 raised to the power minus 5 times 10 into bracket 10 minus 0 plus 10. The reason why I'm doing this is because I discovered that most of the students don't know how to solve. Even if you are given simple question, you don't know how to solve question. That is why I reduce this solution to something that everybody can easily understand. Now 6 times 10 raised to the power minus 5 times 10 into bracket 100 plus 10. You have 6 times 10 raised to the power minus 5 times 10 times 100 is 1000 plus 10. This is indices. Look at the way I solve it. You have 6 times 10 raised to the power minus 5 times 10 raised to the power 30. 1000 is still the same thing as 10 raised to the power 30. 10 raised to the power 30 will combine with what? 10 raised to the power minus 5. So using indices minus 5 plus 3, you get this. 6 times 10 raised to the power this plus 10. At the end of the day, 10 raised to the power minus 2. Don't forget, I know some students don't still know it. It's still the same as 0.01. 10 raised to the power minus 2 is 0.01. Multiplied by 6, you get what? 0.06 plus 1 is equals to this. This is your final answer. Most time you will not see me solving question like this, but I think I solved like 3 to 4 questions and I break it down like this. See, that is very simple. Let's move to the next question. You have to be very careful why solving this kind of question. Let me read it and then I will explain. The ratio of linear expansivity of copper to that of iron is approximately 1.5. A specimen of iron and a specimen of copper expand by the same amount per unit rise in temperature. The ratio of the length is very simple. You need the knowledge of variation to be able to solve some question in physics. You need your mathematics knowledge very well, the knowledge of variation, proportion and variation, subject of formula, and a linear equation as well. They are very important for you. If you don't know them, I'm going to make a video explaining them, but not now. So you need the knowledge. Let's look at how to solve it. So you are given the ratio of your, let's look at it again. The ratio of your copper to that iron, the ratio of the linear expansivity. You have the ratio. The best way is to pause this video and try to solve some question. Then after that, you look at the solution. Now, given that you are given the ratio of your copper to iron, which is what? 1.5. Don't forget that 1.5 is still the same thing as what? 3 over 2. 1.5 is 3 over 2. Convert it to fraction. Then you have this. The ratio means, if you are talking about ratio, you are dividing the linear expansivity of copper to that of what? Over linear expansivity of iron is equals to 3 over 2. Isn't it? Now you cross multiply. There was one time I was explaining the meaning of cross multiplication. Now you cross multiply, you get 2 alpha c is equals to 3 alpha I. So which means that making your alpha c set of formula, alpha c is what? 3 over 2 alpha I. Oh, yeah. So change in length of copper is equals to what? Change in length of iron. Let's quickly go back to the question. I want to explain. Look at it. The ratio of linear expansivity of copper to that of iron is actually 1.5. Then a specimen of iron and a specimen of copper expand by the same amount per unit. Expand by the same. So which means what? Change in length of copper to that of iron. They are the same thing. Now make your change in length set of formula in this formula. Remember this formula. Change in length over original length into bracket change in temperature. Now making it the subject of formula, you are going to get this. Change in length is what? Alpha L into bracket change in temperature. But don't forget that the change in length is the same thing for the two guys, the copper and the iron. So yeah, go ahead and write their formula, which means what? These guys should be constant. And don't forget there is a relationship between alpha C and alpha I. Alpha C is equal to 3 over 2 alpha I. Wherever you see alpha C, go ahead and put alpha I there. So alpha C is there, you substitute the value here. When you substitute it, you get 3 over 2 alpha I LC change in theta is equal to what? Alpha I L1 change in theta. In the question you are given at the same temperature, so which means you can cancel the change in temperature. You cancel alpha, what's it called? Alpha I, then you are left with what? 3 over 2 LC alpha, sorry, 3 over 2 LC Li. When you cross multiply, you get 3 over 2. At the end of the day, you divide both sides by what? 2 over 2 L1 and 3 to get the fraction. At the end of the day, ratio of LC to Li is equal to 3 over 2. Very simple. This solution is self-explanatory enough, so you can look at it. Next question. A metal cube of side 5 centimeter and linear expansivity 2 times 10 raised to power minus 5 per Kelvin is moved from ice water mixture into a boiling water. The temperature in the volume of the cube is, sorry, the increase in the volume of the cube is. Pause and solve this question. Let's look at the solution. You are given the what? Given that you are given the side of the cube. What is the side of the cube? 5 centimeter. And you are also given the what? Linear expansivity, coefficient of linear expansivity 2 times 10 raised to the power minus 5 per Kelvin. Then don't forget the change in temperature is equals to what? 100 degree minus 0 degree. Then the question is, where am I getting my 100 degree and 0 degree? Let's look at the question again. It's moved from ice water mixture. The freezing point of the temperature of ice water here is what? 0, and the temperature of boiling water here is what? 100 degrees Celsius. That is where I'm getting my 0 and 100 from. Now, theta 2 minus theta 1, 100 minus 0. So you get 100 degrees Celsius. The volume of a cube is what? L cube. L raised to power 3. You are given the side. Then the question is, why am I not converting to standard unit, the SI unit? Most times, you look at the options before you start converting, and then you look at the compatibility of your unit. We are going to see that under the heat measurement, latent heat, and the likes. So now let's solve this. Area, volume is what? L cube, 5 raised to power 3, 125. So change in volume is what? V2 minus V1. Oh yeah, you are given alpha instead of what? Gamma. Go ahead and use this relationship. Gamma is what? 3 alpha. Your gamma is 3 alpha. Go ahead and use it. So multiply 3 by your linear expansivity, coefficient of linear expansivity, you get this. Substitute it in this formula. We all know this formula. Change in volume is equals to what? Gamma multiplied by the original volume multiplied by change in temperature. Then you substitute it to get your answer. Just multiply everything here. You get a 0.75 centimeter cube. Why am I using centimeter cube? Because I use centimeter here. It's very simple and straightforward. Let's look at the next question. A density bottle of volume 500 centimeter cube is filled with a liquid and heated from 20 degrees Celsius to 60 degrees Celsius. If 7.5 centimeter cube of the liquid is expelled, the apparent cubic expansivity of the liquid is. This one is under the expansion of liquid inside density bottle. If you have a liquid inside density bottle, we've talked about that one. And it's very simple, straightforward question. Let's look at how to solve it. You can try it, then you look at the solution. So you are given the initial volume of the liquid, the initial temperature, the final temperature. Now, change in volume is what? I've explained this earlier on. The mass of the liquid expelled. And you were given the, which is what? 7.5 centimeter cube. So using this, our alpha, the apparent is what? The volume of the liquid expelled over original volume multiplied by change in temperature. This. Then substitute it, your values. That's 7.5 over 500 into bracket 60 minus 20. 50 times. So you have what? 50 times 30 will give you what? Now that's not how I solve it. Divide both sides by what? Divide the numerator by 3. 7.5 divided by 3, you get 2.5. 30 divided by 3, you get what? You get 10. 10 multiplied by 50, 500, you get what? 5,000. I know some students used to struggle on how to solve this. Most time you will just be pressing your calculator. You don't need calculator to solve what this question, for God's sake. You are just wasting your time using Jamb calculator. You can solve this within few seconds. Now, at the end of the day, 2.5 over 5,000 is very simple. Divide your numerator by what? By 5. Denominator by 5. Dividing 2.5 by 5, you get 0.5. 0.5, now 55,000 divided by 5, you get 1,000. Now 0.5 divided by 1,000, you get this is 0.00005. Convert it to standard form, you get this. Simple and straightforward question. Now another question is, a flask of volume 1000 cm cube filled with mercury is heated from 30 to what? 60 degrees Celsius. If the cubic expansivity of glass and mercury are, you have the cubic expansivity of the glass, you have the cubic expansivity of your mercury, respectively. Find the apparent increase in the volume. Now, this one is not asking of apparent coefficient of expansion. It's asking of apparent cubic. Sorry, find the apparent increase in the volume of liquid. You can try it. Before you try, let me quickly explain it. Now, your liquid will expand, your mercury will expand, and the glass will also expand. Now, to get your apparent, just subtract the two volume, find the difference of the two volume. Very simple. Now, you are given the volume of your glass. This is the volume of your glass, which is what? It is filled with mercury. So the volume of the mercury is also this. Initial temperature, final temperature. So you are given this value. Now the next question, you are given this cubic expansivity, coefficient of cubic expansivity, which is what? For your glass you are given, and for your mercury as well. You should be familiar with this formula. So which means change in volume of your glass is equals to this. Gamma glass multiplied by V glass into brackets, change in temperature. You substitute those values here, which was 2.4 times 10 to the power minus 4 times 1000 into bracket 60 minus 30. And if you solve it, you get 7.2 centimeter cube. The same thing, you calculate the change in volume of your mercury as well. You insert the values given, you get 5.4 centimeter cube. Get your pen. You can as well have your calculator, but I don't encourage calculator. And a pen, a book. While using this tutorial, you can pause it, then you solve it yourself. Now, apparent increase in the volume of mercury will be what? Change in the volume of the mercury minus change in the volume of the glass. Now, mere looking at this, you discover that the change in the volume of your glass is more than a change in the volume of your mercury. So that is why we have negative here. We have minus 1.5 centimeter cube. Yeah, let's look at the final verdict on this solution. The negative sign shows that the glass expands more than the mercury. Therefore, it will appear that mercury reduces in volume. I've explained it earlier on. So it will not look as if your mercury actually expands, but you know that it expands. But at the end of the day, you discover that the volume of your mercury will come down because the glass has expanded the more compared to your mercury. That is why we have what? The apparent change in the volume of your mercury will now be what? 1.5 minus 1.8, centimeter cube reduction. Now, the cubic expansivity of mercury is 1.8 times 10 to the power minus 4 per Kelvin, and the linear expansivity of glass is 2.4 times 10 to the power minus 4 per Kelvin. Find the apparent increase in the volume of mercury in a glass container. This one as well is very simple. To do that, now what they are asking here is find the apparent increase in the volume of mercury in glass container. It's very simple. Now the first step is what they're actually asking for: apparent coefficient of volume expansivity of mercury. That's what they're asking of here. Now to solve it, so you are given the what? This guy. You are given the gamma for your mercury. You are given the alpha of your mercury, that's linear expansivity of your mercury, coefficient of linear expansivity. And don't forget that the coefficient of cubic expansivity is equal to what? 3 alpha. And you substitute that value to get the cubic expansivity of your glass, which is this. 3 times this, you get 2.4 times 10 raised to the power minus 5. It should be minus 5. Sorry about that. 3 times 8.0 is 24. And 24 times 10 raised to the power minus is 2.4 times 10 raised to the power minus 5. I'm sorry about that. Now, you get 2.4 times 10 raised to the power minus 5. The solution is actually correct. It's just while I was typing the indexes. Now, don't forget that your real coefficient of real expansivity is equal to what? Apparent expansivity plus what? The expansivity of the glass. Now, apparent expansivity will now be what? The expansivity, your real expansivity minus coefficient of real expansivity minus the expansivity of the glass. Substitute the value. So you get 1.8 times 10 raised to the power minus 4 minus 2.4 times 10 raised to the power the minus 5. At the end of the day, you get what we have here. Just change the index to minus 5. It's supposed to be minus 5. Let's look at heat transfer. If you're talking about heat transfer is the movement of heat from one point to the other, how it can move, how we can move it from one point to the other, or the process in which it can move from one point to the other. Now, the first one is conduction. Conduction means what? Vibration of the molecules due to increase in kinetic energy of the neighboring molecules. Very simple. Increase in kinetic energy means what? Increase in the temperature of the neighboring molecules. It takes place in solid. Now, the vibration of the molecules. Now, for the conduction, the molecules are not changing their position. The atoms and the molecules of that material is not changing the position, it's not transferring, it's not moving from one point to the other. The only thing that is happening is the kinetic energy is increasing. The neighboring molecules, the kinetic energy has increased, so it is vibrating about its main position. So due to this vibration, the next atoms that is close to it or the next molecules will gain energy automatically. Now that is how the heat will now be transferred from one point to the other. Example, if you have a metallic spoon and you dip it inside your pot, after a while you discover that the heat will have moved from the portion of your spoon that is inside the pot to the handle. So that is conduction taking place in solid. Convection means what? Movement of molecules due to change in density of the neighboring molecules. Takes place in fluid. Now, convection is happens when there is what? Change in the molecules are displacing one another. They are changing. The molecules is changing position. Unlike solid, that the molecules is just vibrating. For convection, the molecules are what? Are changing, are moving from one point to the other. And this takes place in fluid, liquid, and gas. The type of heat transfer that takes place in them is known as what? Convection. Now, I used to tell my student that convection also means what? Conduction in fluid. Conduction in fluid. Okay, let's look at the explanation again. Before, no, I will use the types of convection to explain convection again. Now, the last one is radiation. Radiation takes place in vacuum and it does not require a medium. It obeys the law that states that what? Objects will radiate heat energy at a temperature above 0 Kelvin. Unlike convection and conduction. Now, radiation does not require any material medium and it takes place in vacuum. And for radiation, the intervening atoms and molecules are not heated. You are not heating it. The intervening atoms and molecules are not heated compared to what? To conduction and convection. Now let me quickly talk about radiation. Now let's talk about black body, radiation of black body. Now for black body is a material that will absorb all the radiant energy that falls on it. So which means if you shine light to black body or a black material, so it's going to absorb all the heat energy. I don't know why I'm explaining this because it is not here. So that is that about black body. Now we have some instruments that we can use to measure radiation. We have our thermopile and we also have our radiometer. Now for thermopile is an extension of thermocouple. So if you have thermocouple connected in series and parallel, you get a device that is known as what? Thermopile. You can use your thermopile to measure radiation. Sorry, you can't use it to measure radiation. You use it to detect radiation. And your radiometer, you use it to measure radiation. Radiometer is just like a pyrometer. When I was explaining different type of thermometer, the other one just like a pyrometer. Now, pyrometer is going to compare the color of that material that you are heating at a very high temperature. Let's take for instance a furnace, and then don't forget you have a melter. Let's say you want to melt, you have a molten melter. The color, your pyrometer is going to compare the color. It's going to use the radiant energy in that molten melter That is what is going to use to give us the temperature of that multimeter or furnace, for instance, is using radiant energy. Now, radiation is also different from electromagnetic radiation. Radiation is different from electromagnetic radiation. Don't get yourself confused. Electromagnetic radiation is another thing. Now, this is a type of radiation that comes in place due to what? Interaction of magnetic and electric field. Unlike your normal radiation, you have a charcoal pot, you are heating your pot, you are burning your coal. The kind of heat, you are not close to that place, but the heat is being radiated and you're able to feel the heat. That is known as radiation. It is not electromagnetic radiation. Don't get yourself confused. Now we have type of convection. We have natural convection and forced convection. Natural convection takes place naturally without an external force. Example, sea breeze, land breeze. You are in your room, you open your window and fresh air blows in. That is called natural convection. Nobody is forcing this thing. The natural laws are just forcing natural convection. They happens naturally. Example is sea and land breeze. Forced convection, you are forcing it. It is aided by external force. Example, you have fan, you switch on your fan is blowing, air from one point to the other in the room. So which means the hot air will be blown away and the fresh air will be blowing, the fan will start blowing everything together. The same thing is your hand fan. You are using your hand fan to blow the fresh air. So you are blowing away what's it called? The hot air. You are blowing them away so that the fresh air will come in. Air condition. Sorry, the spelling is wrong. We have the same thing is you have your radiator in the car, radiator fan as well. They are all called forced convection. The next one, let's quickly look at this illustration. We explain sea breeze and land breeze. Now this one is for sea breeze. You discover that in the afternoon when the sun is shining, everywhere is hot, and you have people going to beach, different beaches. Now, why are they going there? They are going there to receive convectional current or convection current. Let me put that way. So let me explain the principle. Now, as the sun is shining, we have the sun here shining on the ground, shining on the earth's surface. As the sun is shining, now the earth will start absorbing the heat. Now, the ground, all this level ground, they have high thermal capacity, which means that they have, sorry. The ground, as the sun is shining, the ground has low thermal capacity, which means that the level at which it absorbs its energy is so small. So as the ground is heated, the layers of the air that is above the ground layers will be hot. Why is it that they are going to have high temperature? It's very simple. You have the ground, it cannot absorb heat that much to that extent. So as the sun is shining to heat, it's releasing back the heat. Now the layers of air above it will automatically gain the heat. So which means the layers of the air above the layers of above the ground will have high temperature. And let's compare the sea. Now, as the sun is shining on the sea, don't forget the sea is having water, and water has so many abnormality in its behavior. Water is so special. Now, this water automatically has high thermal capacity. The thermal capacity, it has what? High thermal capacity and low coefficient. It's having high thermal capacity uh it has high thermal capacity. Oh, in the afternoon that the sun is shining, everywhere is hot. You discover that people usually go to beach and to receive conventional air. It's very simple. Let me explain the principle. This is called sea breeze. During the afternoon, the sun is shining. You have the sun shining. Is shining to this. Is shining on Earth. Now you have the sea as well. Sun is shining. Now the ground has low thermal conductivity. It has low thermal conductivity. Now, due to this fact, it can absorb limited amount of heat. Now, don't forget, thermal conductivity is the ability to absorb heat, Abi. Now, this ground has limited amounts of heat energy it can absorb. And we have masses of air flowing. We have air flowing here. We have air everywhere. So which means that the air above the ground level will automatically absorb some of the heat that the ground cannot absorb. So which will lead to what? Increase in their temperature. As their temperature increases, we have what? Automatically the volume of that air will increase. So which means that they have low density. So the air above this ground level will be what? Having low density. The temperature has increased, low density and more volume, due to the fact that this guy cannot absorb a lot of heat. And it also have what? High thermal capacity. Look at it. High thermal capacity, low thermal conductivity. That is why most time if you are walking with your barefoot on the ground during the afternoon, you discover that everywhere is so hot. Discover that everywhere is so hot. So let's move to the sea. Now, the water is having what? High thermal capacity. Now, this guy will start absorbing the heat. Instead of releasing the heat, water will start. It's not this fish. I'm just using this fish here. So the water here will start absorbing the heat. So the layers of the air above this sea level, the temperature will not be as much as the temperature of these guys. So basically, this one we have what? High density. This one we have what? Low density. The temperature of this guy has what? Has increased. The temperature of this guy will be low compared to this. And naturally, there is one law naturally. Heat will generally flow from a point of what? High temperature to a point at which we have low temperature. So yeah, which means that the air that we have here, so this air will automatically flow to the sea to go and cool themselves, and then the air above the sea level, above the sea, sorry, will flow to replace the one on the ground. So if you are close to the sea, you start receiving that breeze, that convectional, that's convection. You start receiving them. That is why we see people going to the beach in the afternoon. just to cool their body. So automatically we have the currents. This is the direction like this. Then the cold air like this. You have it that way during the afternoon. So let's look at what will happen during the night. So this time is known as what? Sea breeze. Now during the night, the sun is no longer shining again. We have the moon here. So since the moon is not generating any heat, let's look at it. We have the sea. Don't forget that this guy has what? Limited amount of heat capacity. It has released all his heat during the afternoon. Now during the evening, this one that is absorbing a lot of heat, he will later release the heat that is that it has absorbed. So you later release the heat. So simple. During the night, all those heat that it has absorbed, it will release it during the night that the sun is no longer shining. And this one, don't forget, it has released all its heat. Now, which means that the air above this ground level will be cold. The temperature will be small, will be low, compared to the air above the sea. Above the sea, this air we have what? High temperature. So automatically, the air we have, the air above the sea level, the density will increase, will be more compared to the density of these guys. As a result of that, we have reverse flow of current, which means the air above the sea level will quickly run to the ground, and the one above the ground to the sea. So we have the direction the other way around. What I just explained now is known as what? Land breeze. Get the diagram. What can come out of this in your Jamb is very simple. This diagram, understand the direction of the flow of the air. Another thing is our vacuum flux. This diagram you are seeing here is known as what? Vacuum flux or DEWA. It's also known as thermoflux. And what are we using it for? We are using it to prevent heat loss or heat gain by our liquid. You have a flux to prevent heat loss or heat gain by your liquid. Very simple. Let's look at the part of our flux.